Okay, this is the beginning of a series of videos on linear algebra, and we're going to start by reviewing systems of linear equations. This is kind of the bread and butter of linear algebra. The basis of almost everything that's going to go on is going to be, can be tied back to solving systems of equations and linear equations in particular. And the linear equations that you're going to use, you're going to always write them in standard form. So you would recognize a standard linear equation in two variables in this form: ax plus by equals c. It's linear. A, b, and c are constants, and we say they're, a and b are coefficients of x and y. In linear algebra, we're not limited by two variables. We can go up to as many variables as we want, and you're going to run out of letters to use to represent all these things. So what most of us do is we let the variables be x's with different indexes. So we have subscript 1, subscript 2, and then subscript n for the last x variable. So this x1 is taking the place of x, this x2 is taking the place of y, and you can have a z and so forth, but there's just, you could have 100 of these and you'd run out of the alphabet. And the same goes with the coefficients. So instead of a, b, and c, we're going to use a1, a2, a3 up to a sub n. And then this constant on the right side, we're going to call it b. And a system of linear equations is just multiple linear equations grouped together. And in this case, we have two linear equations grouped together, and there are three variables. So x1, x2, and x3. This guy doesn't have an x2, so you could imagine there's a 0x2 in here. But we have two equations, three variables. A solution to a system is for this guy, it's a set of three numbers, x1, x2, and x3, that satisfy both equations. Right? So I think you probably already know a lot about systems of equations, but you may not have seen it in this notation. So let's do an example where we solve a system using one of the techniques that you learned in algebra. This is called elimination. So I have these two linear equations. They're both written in standard form with the variables listed in order. So elimination would involve multiplying one of these equations by a constant and adding those two equations together in order to eliminate a variable. So in this case, I'm going to multiply the second equation by 2. And when I do that, I'll have a 2x1 and a negative 2x1. When I add those equations, the x1 variable will cancel out. So I'm going to multiply 2 times both sides of the second equation, and I get negative 2x1 plus 2x2 equals 4. And I'm going to write down the first equation on top of that. And what you were taught in algebra is to make this a little addition problem, right? And 2x1 minus 2x1 is 0x1. So that eliminates that variable. 3x2 plus 2x2 is 5x2. And 6 plus 4 is 10. So here we can get rid of the x1. So we have 5x2 equals 10. Divide both sides by 5. And you get x2 is equal to 2. So the next step would be to find x1. right? Because you need both numbers, right, that satisfy both equations. So let's plug it into the second equation. Notice that, we multiplied that second equation by 2, but this equation is still valid. I mean, the solutions to the system are solutions to this equation and this equation, right? So we can use either one, or we could also use the first equation. So this equation didn't go away, we just kind of used it to eliminate a variable. And I'm going to plug in 2 for x2 and solve for x1. So it looks like x1 is equal to 0. All right, so let's talk a little bit about this addition thing. So, you were taught to do this where you just write a plus sign, draw a line, and add these things vertically. And I'd like you to kind of maybe pause the video and just think about, why does that work? Why is this okay to do? Because this is going to be something that we're going to use more extensively. So we need to kind of understand why this is okay. So pause the video and I'll explain it when you come back. All right, so this works because we are assuming that 2x1 plus 3x2 is equal to 6. So if I took the second equation and I added the left side of the first equation to the left side, well, that's equivalent to adding 6 to the left side. And on the right side, I'm also going to add 6. So all I've done is add 6 to both sides, right? It's just I added this version of 6 to the left side of this equation, and then you just combine like terms, right? So this is 5x2 and the x1's cancel out. So that's why this method works. It's very neat and organized when you just draw this plus sign, draw the line underneath, and add everything in the column. Okay. So the solution here is an ordered pair because there are 2 solutions. You might think of this as x and this is y, and but in our case, we're calling this x1 and we're calling this x2. All right. So when x1 is 0 and x2 is 2, it's going to solve both equations at the same time. So what does that look like graphically? So let's use our calculator. I'm just going to quickly, I had some stuff in there already. I'm going to quickly graph these. Calculator doesn't want to work for me right now. Okay. So when we're thinking about these equations, remember this is y, right? x2 is y. So if we solve this for y, this equation would be what? 3y equals 6 minus 2x divided by 3, 2 minus 2/3 x. So that's the first equation. 2 minus 2/3 times x. And then the second one, it's pretty easy to see, right, that this is going to be y equals x plus 2. And if we graph that, like we need to set the window first. Oh yeah, my window's all messed up. So let's go from -5 to 5 in the x, scale by 1, and let's go -5 to 5 in the y, scale by 1. There we go. So we got the two equations graphed. The first equation looks like it's in blue. Second equation is in red. And you can see, sorry, my dog's barking. You can see where they cross right here at 0, 2. So this point that solves the system is the point on their graphs where they share a common point. So it's where they intersect. So if a system has a solution, let's say if a system has one solution, then in 2 dimensions, if you have 2 equations, then that solution is an intersection point. You could have no solution. So no solution is going to be 2 lines that are parallel. 2 lines that are parallel, they're never going to cross, so you're not going to get a solution. And you can also have infinitely many solutions. So infinitely many solutions is 2 lines where the solutions are, or say 2 equations where the solutions to both equations are the same line, right? So a quick example would be, if you had 2x plus 4y equals 6 and x plus 2y equals 3, right? So if I just divide this by 2, I get the second equation. Those 2 equations have the same solutions exactly. So these two, this system would have infinitely many solutions because it's just a line and there's infinitely many points on this line.